Okay, welcome back. We're moving on to section 12.3, which is called improved Euler or Runge-Kutta methods. Two separate sorts of methods, but they're very closely related. And yes, in fact, these two words, these two names are a little tricky to pronounce. It's pronounced Runge-Kutta, not Runge-Kutta. This has nothing to do with the 90s metal hybrid music sensation of grunge. And hopefully you can all pronounce Euler by now. But Runge-Kutta is how we pronounce these. And the whole idea was, if we jump back one section back to Euler methods, we had the sort of approximations where we could gain an approximation at a specific time step, maybe k plus 1 time steps away from where we started, by looking at a previous approximation, adding delta t, then the nonlinear function on the previous term, and the nonlinear function was evaluated at like k time steps away from where you started in time. So this was a really nice first order method for us, and it's really easy to implement in coding, but since it's only first order, we don't get like the world's best approximations. We would like to get better approximations. So the point of this section is to get some sort of improved approximation or higher order method that doesn't require too much more difficulty in the coding and computational power. And that's why we call it improved Euler in the first case, and then two mathematicians came around, Runge and Kutta, and they kind of generalized this method to a very wide variety of methods that can all be implemented very easily and all have like very high orders. You can get Runge-Kutta methods of whatever order you really want. It's not too hard to find them. And the way that these are going to work is that instead of, if we jump down here to the approximation, this is kind of the Euler approximation, right? If we resolve this for t plus delta t, that evaluation, you gain the Euler approximation. And it all comes down to this term right here, where we've evaluated the nonlinear function at the previous approximation. Maybe I'll write that down here. Evaluated n sub t at previous approximation. But in fact, the value that we should be evaluating nt at really should be kind of either like the midpoint between y tilde and then the next time step, like our current time step and the future time step, because y has a different value there, which means n is going to have a different value there, which means our approximation could possibly get better if we knew what that value would look like. Or we could evaluate, in fact, at any time between the current time step and the future time step. So I guess the takeaway point is, what if this evaluation happened at a time between t and t plus delta t. So what if that evaluation occurred sometime in the future, but not quite at our next time step? But that seems like a really strange thing to ask, right? Because I think a lot of you are saying, well, why not just make your overall time step half as large, and then you just get an Euler method with a smaller time step. And that's really not what happens, and you don't get the same sort of approximation if you just take delta t smaller and repeat Euler. It truly gets better. You get a better order if you end up talking about evaluations that are occurring at an intermediate time step. And this is the whole idea with improved Euler. If we jump over here down to this next line, you can start to see what's happening here is that I'm giving myself a time, the current time I'm at t plus my time step, but I've given myself the parameter epsilon. So I'm saying, hey, let's actually evaluate n at a slightly future time, but epsilon's less than 1, right? It's something between 0 and 1. So evaluating at a slightly future time, well, I need to know my approximation at the future time. So maybe that's the tricky thing is what is the approximation at the future time? Is this if I only know y tilde at t? Right? What should that somewhat future time step be if I only know y tilde at t? Well, this is kind of the funny thing, is we use the Euler method here. So we use the Euler method to give ourselves like a miniature time step in between the two other times, and then we only use that for evaluation into m. We don't use that as like a true time step parameter. And in fact, it's a little bit more complicated than that, because what we can do is we can actually take like an average value of a few of the time steps in between, right? So we can consider multiple values of epsilon here and repeat the n for like 2 or 3 different choices of epsilon, but each one of the y tildes on the inside there is calculated with Euler. But if we repeat it and then take like a nice weighted average, we can get a better version of n overall. But anyway, this is the Euler-like method. If I decide to replace this approximation, at least with the Euler approximation, you can see what I have here then is kind of an iterate of this nonlinear term. But then, yeah, if I want to average maybe n at y tilde, so the initial time, plus n with a future time, on a future time, then you get like a better approximation to the true n, because suppose the two of them agreed, well, that means that n is relatively constant over that interval, which means that the average is just going to give the constant value of n. But if they disagree, then depending on how you take your average, you're going to get a better approximation to what n should look like in that interval. So I'm going to start with the improved Euler method here, which is basically just doing this with two weights, right? We're going to choose some epsilon, which we're going to push ourselves forward and give ourselves an approximate n at the forward time, as well as the approximate n at the original time. And then we're going to take a weighted average, and that's what the W1 and the W2 is, and that's why I'm dividing by their sum. So this, in some ways, you can think about this. This would be the regular, this is the regular Euler approximation to n sub t. And the improved Euler says, hey, I'm going to give myself the ability to get a second approximation. So this is a second approximation to n sub t at some time slightly in the future here, right? So I have an approximation a little bit more in the future. And then if I compute a weighted average of those two approximations, then I use that in what looks like a traditional Euler time step, right? So it would look like Euler if, suppose W1 was equal to 1 and W2 was equal to 0, then what is that? That's exactly Euler, because I'm not really doing a weighted average because I'm getting rid of my future time. But if I allow W2 to be something non-zero, then I have a nice weighted average there of two approximations to n. And what we have then is a few examples. We have the Euler method, like I just talked about, but we have what's called the midpoint method. And that would be actually where we take W2 to be equal to exactly 1. So we're only looking at the future time approximation to n. But that future time occurs exactly 1/2 time steps in the future, right? And that's why we're calling this midpoint method, because I'm saying, okay, let's shoot ahead 1/2 times in the future, and then my method looks like the following, right? So I have really two iterates of n along with a 1/2 on the internal piece. And this is actually also only first order, so for many reasons you wouldn't really want to use this unless you have a very good reason to think that it's going to give you a better approximation, since it is only first order, like Euler's. But we can get some better methods. So Hoyne's method over here is a second order method, and that's where we're going to actually have two weights, right? We're going to give equal weight to the original time and the future time, and we're actually going to jump all the way to one time step ahead, right? So this basically says, hey, let's average our current approximation with what n would be if I already had jumped ahead. And then I'm going to use the average of those two n's, which is probably a pretty good choice of what n should be over that interval, and that's where we get away with a whole new order. And then you can actually do something called Ralston's method as well, which is when you weight the future time a little more heavily than the initial time, but the future time isn't pushed all the way like epsilon equals 1. It's not pushed all the way to the full delta t. It's pushed to only 2/3 of delta t. So it says, hey, I'm going to approximate n 2/3 times in the future, and then I'm going to weight that twice as heavily as I weight my original n. And then I'm going to give myself one time step forward. So it's pretty interesting. You get a full class of methods here, and some of them are still first order and some are second order. We then jump over to Runge-Kutta methods, and the Runge-Kutta methods is really the same sort of idea, except we're not gonna give ourselves only two averages of n. We're going to give ourselves j averages of n. So all of a sudden in Runge-Kutta, we're going to say, hey, let's just jump out really far, or like discretize this interval. You know, there's t, this is some interval, there's t plus delta t. Let's give myself j different points on this interval, each of which at these points I'm going to approximate n at t at each of those purple points. And if I take a weighted average of all j of those, then I'm going to get something that's really close to what n should be. And the way that we talk about these Runge-Kutta methods is with something called a butcher tableau. Butcher's capitalized because it's named after a person, not a butcher. And I don't think these are terribly useful. You could just describe all of the constants that you're going to use in Runge-Kutta directly, but this is a common way that it gets notated, so I better show everybody it. What we have here, these are the same epsilons and w's that we had in our Euler methods, or improved Euler methods. It's just that now we have m of them. Okay, right. So that's why I'm calling it an RKM method. That stands for Runge-Kutta method of m stages. So I'm allowing myself to discretize time into m different steps and compute a lot of different weights. You'll see that there's actually way more than m weights here. I guess here it's like m squared divided by 2, maybe m times m minus 1 total weights or something like that, divided by 2, and then I have m weights at the bottom. So actually these, maybe I'll describe this here, these are the same epsilons, same epsilon as for improved Euler. So those aren't too surprising. They just tell you how far to look in the future. But the W's here are describing, these are weighted averages at intermediate steps. Right, so the idea is that at each step I could actually compute a weighted average of the previous steps. So that's why you start with only one weighted average of, the epsilon 1 step, then you can have up to 2 weights on the epsilon 2 steps because it considers the 2 and the 1, and then so on. And you consider weighted averages of each previous step as you compute this, and then finally the bottom row is the true weighted average for the actual time step forward. So this is the true weights for the final time step, which is like yk plus 1 equals something which depends on yk, right? So that very last time step where you're producing yk plus 1, that's what the bottom w's are coming from. But that's just a way of representing these constants. Let's actually talk about the Runge-Kutta method. So it's going to look a little bit ugly, but it's actually, we're going to parse it and then it's not going to be too bad. I'm going to keep the butcher tableau up there. So let's parse it and we'll be able to see that this isn't too bad. So we're starting with the same IVPs like we always would, and we're still giving ourselves the label that y tilde sub k is the approximate value of y at the kth time step from where we started. So we're going to do a butcher tableau with epsilon 1 equals 0. Okay, so understandably, I had put an epsilon 1 in the butcher tableau. For a Runge-Kutta method, that's always going to be equal to 0. Technically, you could allow yourself a non-zero epsilon 1. It's probably not a very good idea. But the Runge-Kutta method of this mth stage, which is a result of this butcher tableau. Okay, so we're going to be paying attention to how these constants up above behave with the Runge-Kutta methods. It's the recursively defined sequence where, no surprise, we start where we start, but let's look try to do one time step in the future, or suppose that we've made it to y sub k. Where do we go? Well, what happens is we're going to compute a j, right? This is a j approximation. So the jth approximation to n sub t. So this is only an approximation of the right-hand side of the original IVP, and it's the jth approximation of those. So we're going to compute a total of m approximations to n sub t at the yk plus 1 time. Okay, so to give myself the k plus 1 term, which is down there, right? To give myself that term, I'm going to compute m approximations to the right-hand side. And those m approximations themselves are computed recursively, okay? So Runge-Kutta says each of these m approximations is going to be computed recursively. You'll see I put a j there, and that j shows up right here, and here, and here, and here, and here. So each of the j's. So as if I start at j1, that means that this is n at t naught plus whatever k was, plus epsilon 1, which we've already noticed was 0. And so this is t naught plus k delta t, and then we have y tilde sub k plus, that was already 0. This is exactly the first approximation to n, right? So the j equals 1 case, this gives exactly n sub t naught plus k delta t evaluated at y tilde sub k. That looks exactly like the Euler approximation to n, right? But if we moved up to j equals 2, for example, then all of a sudden that's a 2, 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 and that's a 2. And all of a sudden we're on the second row here, where now we care about epsilon 2 and w21. So this epsilon 2 here, maybe it's 1/2. This becomes t naught plus k plus 1/2 delta t. So I've moved 1/2 time step in the future. Maybe epsilon 2, oh yeah, we just decided was 1/2. Maybe w2 was 4 for some strange reason. Fine. So we set w21 to be equal to 4, and then we have the original weight on this n sub k plus 1, and then we have the 4 as well, and they both add together. Oh yeah, and this is the bottom weight here is, this should be ji as well. So that's the sum of all of the j's. The wi in the bottom is only there, so that's definitely a typo. You should put a ji there. I'll make sure to update that typo in the book itself. Okay, so but maybe W21 is a 4, then you have a 5 on the bottom, and you're averaging two of those. So and then you just step up J. Every single one depends on the previous. Okay, but then maybe you've gone through all that work, you've gotten J out of it all, and then you're over here, and so you have all of your n tildes, which are your approximations to n. You're sitting over here. You then finish by computing a weighted average of all of those n tildes, and that's coming from the bottom row here, weighted average on n tildes. So now you're computing a weighted average on a bunch of these, which themselves were computed recursively, and then you move yourself one time step in the future. Okay, so this was a very, very formal introduction. It was very broadly described. This Runge-Kutta method, I'm glad I introduced it to you, but what is actually important is the following Runge-Kutta method. So it's specifically this butcher tableau is the Runge-Kutta method. So if anybody ever tells you to use the Runge-Kutta method, capital T, capital H, capital E, the Runge-Kutta method, also known as RK4, we're thinking about this butcher tableau in particular. And because of that, because it's so important, I actually provide that one for you. So the definition, RK4, the Runge-Kutta method. So I provide that one for you, and I make it everything very clear what the order is that you should be calculating everything in. What you do is you just start at y0 like we always do, and then at each time step we have 4 approximations, 4 recursively defined approximations to n sub t. So at that specific time step, we're going to have 4 recursively defined approximations to n sub t. They're given by the following, right? And you just have to follow. That's n sub k plus 1, 1, which is right there. That's n sub k plus 2, 2, 1, 1, 1, 2, and 1, 3. So they each depend on the previous. And then at the very end, we add them all up, and we take a 1, 2, 2, 1 weighted average of all 4 of those. So this isn't too bad, the true RK4. It's not too bad. You just have to make sure you code it correctly, and you make sure that each one of these is recursively defined on the previous one. Then I have a remark to just make sure that everybody knows this is what everybody talks about when they say Runge-Kutta. It's this one right here. Now this is great because it's a 4th order method. So that makes it better than the linearization method, considerably better, right? Because linearization, which in some ways definitely is harder to code than what we have here, linearization was only 2nd order. So this is twice as good in order as linearization, and the coding is considerably easier. So I have one example of RK4 here, just so that everybody can see how we would do it. I only go out to 2 steps because otherwise, things get really crazy. So we're gonna start with n, right? N sub t of y is just the square root of t plus y, and we initialize at 1. So what we have to do for RK4 is we have our y tilde 0, which is just where we started, and then to get our next step, so we're moving from y0 to y1, I need 4 approximations to n, and this is approximations to n sub 1, right? And so these 4 approximations, the first one is just n evaluated at t equals 0 and the previous y, so 0 plus 1, because the previous y was y0, which is 1. And then these are defined recursively, right? So I'm going to use the previous number in my next recursion. So then I move forward by 1/2 time steps. My delta t is 0.1, so I move forward by delta t. I also take the 1. This 1 here is this one, right? And this one here is that one. Okay, so those ones are y0. I have those ones, and then I also add 1/2 plus 1 time step on the previous n. So in fact, this whole term is like an Euler approximation with 1/2 delta t instead of delta t, right? So that's why I have 1/2 delta t. It's an Euler approximation using the previous line with 1/2 delta t. And that gives me a new approximate n. I then repeat this, right? So I repeat this still with a 1/2, but I'm using, this should be I don't know where that 2 came from. This should be a 4, 8, 8, 1. It's coming from the previous line. So I repeat it from the previous line with my previous n, and this is still like an Euler approximation, but the previous n, and then I repeat that one more time. There's my Euler approximation with yet the previous n, and then that gives me 4 n's, which I take in their weighted family, the weighted average of the 4 n's, right here. So 1, 2, 2, 1 is my weighted average divided by 6, and that gives me my next y, which in this case is approximately 1.10492. I then repeat this process, right? So I wanted to make it clear how you would then repeat this at the next time step. So this is at the next time step. I'm going to repeat it. And keep in mind that because I've shifted my time, now I'm k is 1, that's one time step ahead, I have to shift each of the k's right here to a 1. So the previous line, all of those k's were zeros. Those were these zeros. When I shift ahead in a time step, all of those become 1s. And then I do the same procedure where I get an approximation to n. I use that approximation in Euler with a 1/2 time step to get a new n. I use that approximation in Euler with a 1/2 time step to get a new n. Then I use that approximation with a full Euler time step to get one more n. So I have 4 approximations to n, and then I consider the weighted average of all 4 of those approximations to give myself the number at the second time step. And this seems really tedious, and it is really tedious when I write it down. Believe me, I had no fun teching this up into a book. But if you set up a computer to do this for you, all it has to do is iterate and keep track of k, keep track of 0, 1/2, 1/2, 1, and then use each previous n on the last one, and then average all of them to give you your next y. So in that sense, it's actually really, really efficient on a computer. Here you can see how it approximates the solution. The solution's there in black. And then if I use Lagrange interpolation on it, you can see like the amount of black that is differing from the red here is just almost negligible. Like it's there, but it's so hard to see because these points are so well approximated. This is what a fourth order approximation gets you. So thanks for sticking with me. I know Runge-Kutta is a little bit tricky, but I think if you just look at the specific method right here, freeze frame that and really try to memorize it, internalize what's happening, you'll be just fine. So anyway, I'll see you in class. Bye.